Fahrenheit into Kelvin. So you can use this particular derivation. And similarly, this is also the same derivation which you can use. C by 5 F minus 32 by 9 is equal to K minus 273.15 divided by 5. So this is the you can say the formula for converting from Celsius to Fahrenheit to Kelvin. So in this particular case, we will be only going for conversion from Celsius to Kelvin actually. Okay. Most of the thermodynamics, we may have to change the degree Celsius temperature to Kelvin. We won't be using Fahrenheit temperature, but if in any question it is given, or if you are referring to some book where it is given, so you should know how to convert it into that particular Fahrenheit into Kelvin or Celsius, and you can use this particular equation. Let us move to the next topic. Now this is a question which is given here. You can read the question carefully. The pressure in a gas, the pressure of a gas in a pipeline is measured with the help of a mercury manometer having one limb open to the atmosphere as shown in figure. So you can see it here. This is actually open to the atmosphere. This limb is open to the atmosphere. If the difference in height of the mercury in two limbs is 562 millimeter, so basically the fluid which is inside this manometer is mercury, Hg. Hg stands for mercury. So this value of Z, which you can see, this is the difference in the level of mercury. This is equal to 562 millimeter. Calculate the gas pressure. So what's happening? There is a pipeline. This is a gas which is flowing here. Okay, this is the gas, and this gas is exerting pressure here, and that is why the level of the mercury goes down to point A in the left limb and rises here in the right limb. Okay, so this much from say you can say from here to here, this value is Z, and this is the increase in the level of the mercury in the right limb. The barometer reads 760 millimeter of mercury. So what do you know what is a barometer? Barometer is a device for the measurement of atmospheric pressure. So barometer measures atmospheric pressure. I think somebody wants to join, so I will have to shift the screen. Bill. Okay. And the acceleration due to gravity. This is the value of G, acceleration due to gravity. And the density of the mercury is given as 13,640 kg per meter cube. So this is the numerical problem, and what we need to calculate is we need to calculate the gas pressure. You can see it here. It is the gas pressure which needs to be measured actually. So in the next slide, I have calculated, I have solved this numerical problem. So first thing that is given to us is atmospheric pressure, and the value is 760 millimeter of mercury column. Normally, if we see, then this value is 760 millimeter of mercury column. But in this numerical problem, the atmospheric pressure is given as 760 millimeter of mercury column. Okay. So now you can see it here. See, if I take this particular cross section here, A, and this B, okay, both have the same separated by the same fluid actually. See, here you have the gas, okay, and here we have the mercury. So we have to see that at which point in both the limbs there is a single fluid, or there is a separation of one fluid. Okay, so here we have the gas, and here all together here up to this particular point we have the mercury. So we have to locate this particular section. So this is the section here, and above this we have given as the height of the mercury is Z, which is equal to 56.2 centimeter. Actually it is given as 562 millimeter, so it is 56.2 centimeters. So we have to calculate And you can see there we have the atmospheric pressure, because this end is open to the atmosphere. This is open to the atmosphere. Here the atmospheric pressure is acting. Okay, it is atmosphere. So what is the total pressure at A? See, I can always say, because the level at A and B is same, so pressure at A and B will be same. And pressure at A, if I have to calculate, that would be given by, or rather, pressure at B, I will change it to pressure at point number B. Okay, this is point number B. One is the pressure which is acting here due to this level of mercury. Okay, this is the level of the mercury which is above this point number B. And also there is a pressure, atmospheric pressure, which is acting over it. Okay, so the total pressure at point B will be rho gh for the mercury plus P naught. P naught is nothing but atmospheric pressure. P atmospheric. Okay, so this is the value of the atmospheric pressure. So once again, what I can do is I can write it as PB. Actually, whether you write PA or PB, they are one and the same thing. But because from PB side, if I am measuring the PB, it's quite easy to understand actually. So now I can use this particular formula for the mercury. Okay, what is the value of rho for mercury, which is density? It is given here 13,640. So first of all, I am writing this particular value, this much kgs per meter cube, multiplied by the value of G, which is 9.79 meter per second square. And here, this is the value of H for the mercury. So I am taking it in meters, 0.562 meter. Plus, what is the value of the atmospheric pressure now? So atmospheric pressure, once again, we can calculate it in terms of rho gh. Okay, so this is once again the density of the mercury multiplied by G multiplied by the height of the mercury column, equivalent to the atmospheric pressure. So this is once again meters, this is meter per second square, and this is kg per meter cubes. So now we can solve it. There are two terms, the first term and the second term. In both the cases, this and this, they are common in, uh, so they can be taken out of the bracket sign. Okay, and inside the brackets we have 0.562 and 0.761. Okay, we can calculate this particular value and we will get this answer, this much kgs meter per second square into, now what I have done here is, this is basically, you can see, per meter square. I think you can give a try to it. Yeah, I will tell you. See, you can see it here. This is kg per meter cube and meter per second square. So this meter will cancel out, and here we will have the square. Okay, and this meter is there, and per second square. So I can take this meter, second square, and kgs together. Okay, so this we get this particular value, kg meter per second square, and in the denominator here we are left with the meter square, so it is meter square. And this value kg meter per second square is nothing but newtons per meter square. So I get the value, and newton per meter square is nothing but the pascals. Okay, so I get this value. I have rounded off here 1.76 into 10 raised to power 5. And then if I divide this value in Pascal by 10 raised to power 5, I will get the answer in bar. So the pressure at B is 1.76 bar, and that is also equal to the pressure at point A, or that is equal to the gas pressure also. Okay, so this is how we have calculated the pressure. So it's a simple numerical problem based on the uses of pressure relationship, which is given by P is equal to rho gh. Okay, so the pressure which we have calculated here is gauge pressure, or absolute pressure, or atmospheric pressure, because there are three types of the pressures, you must remember that. So which pressure we have calculated at point number A or B? Can you tell me? Okay, let us see it here. See, I
Gauge
am
pressure.
no, it is not the gauge pressure. Let us see. See, when I say P at point number A, okay, you can see it here. This is the gas which is flowing in the pipe actually, okay, and we are calculating this pressure of the gas here. This is the pressure of the gas here with the help of this manometer. This is a YouTube manometer actually, okay, or a mercury manometer. Now you see at point number B, what we are calculating? We are calculating the pressure due to this value Z, okay. Now this value Z corresponds to the gauge pressure. When I am adding this atmospheric pressure into it, that means I am calculating the absolute pressure of the gas. Okay, so this PA is absolute pressure, which is equal to P gauge plus P atmospheric, and this P gauge was actually equal to rho G. You are given with Z. This P gauge is Z value plus P atmospheric. P atmospheric is once again rho G into 0.761, and now it is for mercury. So that is, so this part, if I am calculating, if I am putting the value of Z which is equal to 0.562 meter, if I am calculating only this value, then it is equal to the gauge pressure. Okay, if I am adding atmospheric pressure into it, then it then the sum of these two becomes the absolute pressure at A, which is actually equal to the gas pressure. Is it clear now?
It's clear.
It's clear. Okay, so I will proceed further now. Now I am going to the next topic. It is on work and heat transfer. Work transfer and heat transfer. Now let us read these lines here. The first line is a closed system and its surroundings can interact in two ways. One is by work transfer and another is by heat transfer. Okay. Work transfer, we will say that we represent work transfer by W and heat transfer by Q. These are called energy interactions, and these bring about changes in the properties of the system. So whenever there is these two interactions are there, that is work transfer as well as heat transfer, they will bring some changes in the properties of the system like pressure, temperature, volume, etc. For example, if there is, you can consider a closed container. Suppose this is closed and the mass is fixed here. This is a gas and its mass is m, and the pressure is inside, let us say P1. Okay, and if I say that its temperature value is 2 bar, okay, and temperature is, let us say, 30 degrees Celsius, I am taking it as a closed container. So this mass of gas is going to remain fixed. Now what I do, I supply heat to this container. Okay, so what will happen, because the heat is entering into this closed container, so pressure, the volume is going to remain same. So during this process, V1 will be equal to V2. There won't be any change in the volume of the gas because the container can be considered as rigid. Rigid means you can't change its dimensions. But what will happen if you are adding heat to it? The pressure will change to, let us say, uh, pressure will change to P2 and the temperature will change to T2. And because we are adding the heat, volume is constant. So I can say that the pressure may become 3 bar and the temperature may increase to, let us say, 60 degrees Celsius. So what are these two? This is the property. This is a property. So when heat interaction is there, means heat is crossing the boundary of the system. Though I have not shown here, I can say that this is the boundary of the system. Okay. So my focus is on the gas. I am studying the gas. So uh, that means here you can say the heat is crossing the system boundary and is getting added to the gas, and it is changing the two properties of the system. One is pressure and other is temperature. Okay. In thermodynamics, work is considered as occurring between the system and the surroundings. So it is work transfer. Okay. You will never say that it is work or heat. You will always call it as work transfer or heat transfer. Mind it. Okay. And now this definition is very important. Work is said to be done by a system if the sole effect on things external to the system can be reduced to the raising of a weight. Okay, if a system is doing some work, and by doing this work it can raise some item, raise some things which is external to the system, then we say work is done by the system. And this is also important, the weight may not be actually raised, but the net effect external to the system would be that of raising a weight. Okay, we are not raising a weight exactly, but this effect of transfer of work can lead to the raising of a weight. Only then it will be known as the work done by the system or work transfer. So let us see an example. You can see here. Here we are showing a thermodynamic system. This is the thermodynamic system. I am denoting it by TS. I am not writing in full. Thermodynamic system. And what does this thermodynamic system comprises of? This comprises of a battery and a motor. And this motor has a shaft, and at the end of the shaft there is a fan. So uh, actually what is happening when the energy is supplied by the battery to this motor, okay, this shaft is rotating. This shaft is rotating, and the fan also starts rotating along with it. So basically the work is going out from the system, work is crossing the system boundary in this direction. Okay, so it is the work done by the system on the surroundings. All right. And now we would like to see, can I change this system to such a system where this system is capable of raising some weight? So let us see on the right hand side. Once again the same system is shown, and instead of this fan, the fan which was here available here, instead of that now we are using a pulley, and a rope is wound on the pulley, and a weight is hanging with this rope. This is the rope here. Okay, so when this shaft will rotate now, when we will supply the current from the battery, the shaft will rotate and the pulley will be moving. When the pulley will be rotating, it will be able to lift the weight. So that means this system which we are considering, which is comprising of a battery and a motor, is capable of raising a weight. So this is basically the definition of the work transfer in thermodynamics. In your school classes, you must have studied that work is given by W is equal to F dot S, where F is the force, and you take the dot product multiplied by the displacement, means F into F dot S. So it is the dot product of force and displacement. This is what you get. And you remember the unit of force. Unit of force is Newton. Unit of displacement is meter. So the unit of work should be equal to Newton meter, and this Newton meter is actually joule. Okay, so Newton meter is joule. Work is basically a form of energy interaction only. Now sign convention for the work. So now we will discuss about the sign convention. So what we are considering, we have a system here, and this system, the work is moving from system to the surroundings. This is the value, this is the direction of the work. So it is the work done by the system. Okay, it is the work done by the system. So whenever we are considering work done by the system, just a minute. Okay, whenever we are considering the work done by the system, this is always considered to be positive. So you can see this is the work done by the system, and this is the work done on the system. So this W is entering into the system. So I will say that it is negative. Okay, so you can see here I have written work done by a system is arbitrarily taken to be positive, and when work is done on the system, it is taken to be negative. So both the situations I have told you, and the symbol for the work is given by W. Now let us discuss about the PDV work. I will not show you this slide. I will go to this particular slide. So now I am going to discuss about the PDV work or the displacement work. So PDV work or the displacement work. Now you can see what I am considering here is I have a piston cylinder device. Okay, and the initial position of the piston is here. This is the piston actually, and its area of cross section is A. Area of cross section of piston. This is given as A, and inside this is actually cylinder. Okay, this is cylinder, and inside there is a gas here, and the pressure of the gas is P1, volume is V1, temperature is T1, and this is the boundary. This is the boundary. So inside the boundary there is gas. So our thermodynamic system is the gas, and this gas is now in a thermodynamic equilibrium state at this particular point. So what I have done, I have shown this coordinate here on the PV diagram. This is the state point 1, because the pressure is known, the volume is known, the temperature is known. So I can always locate this particular point on PV diagram or TV diagram or VT diagram. I need two properties actually. Okay, then uh, now due to some reason, for example, if I supply certain amount of the heat here, say Q, what will happen? The Because we are supplying the heat and the boundary is flexible here, because there is a piston, frictionless piston is there. Okay, so let us say that after supply of heat, the piston reaches this particular point. This is the final position of the piston. I call this as the state point 2. Okay, and now the boundary has moved up to here. This is the position of the boundary now. Okay, so gas has expanded up to here. Now what is happening? Now the final pressure is P2, the volume is V2, and the temperature is T2. So now I know the final conditions also, and you can see because the volume has increased, so you can see the volume is increasing in this direction. But when we are supplying the heat, when the gas is expanding, the pressure will drop down. So we have considered the pressure has gone down. So this is the value of the pressure P2. This is P2. Here you can say this is P1, and here the volume is V1. Okay, and here the volume is V2. Now what we are considering, because what we are going to calculate is the PDV work. This you can read it here, PDV work or displacement work in a simple compressible system. When I say simple compressible system, it means either it is a piston cylinder arrangement or such a system for which the boundary can, for which the boundary is flexible. For example, if you have a balloon with you, and if you are filling the air inside this balloon, what will happen? It will, its shape will change. So actually, uh, after filling the air, uh, means there is change in volume and pressure. So we are trying to calculate PDV work for such systems where the volume or the pressure will change or the temperature will change. But it's a, always remember that it's a closed system. Okay. So I hope this is clear. Now what I am considering is the process is quasi-static. Quasi-static means I am considering this process 1 to 2, which is taking place inside the piston cylinder device. Okay, so this is a quasi-static process. That means all the states are in quasi-equilibrium or almost equilibrium. When I say quasi-static or quasi-equilibrium, it means I know each and every state. I have told you this particular definition. I know the path. This path is now known to me through which the piston or through which the system is passing or through which the gas is going. Okay, so I know the pressure and volume changes at each and every point. Because it's a quasi-static process, it's a very slow process. Okay, now what I do, I consider a very small volume here. This dv volume I am considering, you can see it here in the PV diagram. Okay, this volume I am considering, this volume is given by dv. Now, and the pressure here is P actually. And here I have shown this position in the piston. This is, I am showing the position B, B and C, C. Okay. So this is the position. Now what I am saying is, just a minute. What I am trying to say is that at the position BB, the pressure exerted by the gas is P. Okay. The pressure exerted by the gas is P. Now I want to know what is the force which is acting on the piston, because BB is showing some position of the piston and it is moving with a very small displacement which is given by dl. Okay, when the pressure is P only. Okay, so from BB to CC, the pressure is P and the displacement of the piston is dl. So let us see what is the pressure which is acting on the piston. So let us see here. Now I am interested in calculating the force which is acting on the piston. What is the force? Force is the product of pressure into area. Pressure into area. And I know the area of the piston is small a. This is the cross-sectional area. Pressure has a unit Newton per meter square. Area has the unit meter square. So meter square and meter squares cancel out and I am left with Newton only. So which is the unit for force. So I am able to calculate the value of the force which is acting here. Force which is acting here is F, which is given by P into A. Now I am interested in calculating this infinitesimal work. Infinitesimal work means very small work which is done by the piston, and it is equal to F dot dl. F dot dl. So in the next line, what I will do, I will put the value of F here, which is given by P into A, and dl is the displacement. And if I will combining uh, A and dl, what is A into dl? A into dl is dv. Okay, A into dl is dv. So I get this value of delta W as P dv, and this is the displacement work. So delta W is equal to P dv. So this is the expression which is important. Even if you don't know its derivation, that is not required. That is only for explaining you people. Now this is the value of delta W. Now there is a particular reason for which I am using this type of the delta here. Sometimes you must be knowing you may use dt. Okay, and this small d is showing the differential of this temperature T. But here also, when I am using this delta, it's a some sort of differentiation, small change in W, small change in W, which I am interested in calculating, and that is given by this value of PDV. So let us see further. I will tell you why there is difference between this D and delta later on. So this is the expression here. Okay, this is the expression. Now, if I want to calculate, just try to focus on one more thing. See, this is delta into PDV. This is on this diagram. If you will see here, this is the pressure. I am saying that during this process from here to here, okay, this process, the average pressure here is P. Okay, so this is actually, this area is P into dV, because this value is dV. This is dV. Okay, so the area of this rectangle is PdV. So it means area under the curve will give me the total work transfer. This area which I have highlighted is nothing but PDV. And if I want to calculate the total work, what I will do, I will take this particular value of delta W, integrate it between 1 to 2. Here also I will integrate it between 1 to 2, and this value on integration will be written as W, or work transfer, for the process 1 to 2. So this is work transfer for process 1 to 2. So you have to write in this particular fashion. First you will write W, then you will write 1, then you will write 2. So it means it is work transfer for the process 1 to 2. And on the right hand side, this is the integral from 1 to 2 of PDV. So this is the final equation that would help me in calculating the work transfer for a particular process in a closed system. Now, the above equation is valid for, it is valid for closed system, one thing. Second thing is quasi-static process, also called as reversible process. Okay, and when there is not external pressure, you can say when there is resistance at the boundary, resistance at the boundary. Now, where is the resistance in this particular case? You know, this is the piston cylinder arrangement. This is the piston, and here outside there is a pressure which is acting, and this pressure is atmospheric pressure. Okay, so this is the resistance. When the piston is trying to move forward, there is a resistance in the form of atmospheric pressure which is acted at the outside of the piston. So it means there is external resistance at the boundary. Okay, now suppose if this resistance is not there, if it is not there, then what this process would be known as? If there is no resistance, then the gas will expand freely. The gas will expand freely, and this process freely against vacuum, and this process is known as free expansion. Okay, so this equation of PDV, which we have derived just now, this is not valid for the case of free expansion process. Now, the various quasi-static processes for which we can use this particular equation are: the first one is constant volume process, the second is constant pressure process, also known as isobaric process. Another name for it is isopistic process. Okay. The next one is the isothermal or constant temperature process. The fourth one is the reversible adiabatic process. And when we say adiabatic, it means there is no heat transfer, no heat transfer within the system, means no heat transfer from the system to the surroundings or from the surroundings to the system. Okay, so that is a reversible adiabatic process. Then polytropic process where PV raised to power n is equal to constant. For reversible adiabatic process, when I am writing this particular expression, this is PV raised to power gamma is equal to constant, and you might be knowing that gamma is equal to Cp by Cv, where Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. The value of gamma is equal to 1.67 for a monoatomic gas. Uh, Gamma is equal to 1.67 for monoatomic gas, it is equal to 1.4 for diatomic gas, and the value is equal to 1.33 for polyatomic gas. Okay. Now let us calculate the value of the work transfer in few of the processes. The first process which I have considered here is constant volume process. So you can see it here. Uh, this is pressure volume curve for a constant volume process. So constant volume process is starting from this particular point, ending at this particular point, or it could be starting from this point and going in the upward direction. So both are constant volume. Only thing is, in the first case, in this particular case, the pressure is going down, whereas in the second case, the pressure is increasing. That is the only difference. Constant volume, as I told you, is also known as isochoric process. Okay, isochoric. So delta W, so I have to calculate the work transfer for this particular process. So delta W is equal to PdV. I can integrate this equation between 1 to 2, and on the right hand side I can also integrate it, this PdV term, from 1 to 2. But I know that the volume V1 is equal to V2. You can see it here on this diagram. Point number 1 and 2 are on the same vertical line, so it is equal to constant. Volume is constant because the process is constant volume process. So what is the value of dV? Dv comes out to be 0 in this particular case. So you can calculate the value of the work transfer, which is equal to P into value of dV is 0. So the work transfer in this particular case is 0. So that is a constant volume process. In a constant volume process, work transfer will be equal to 0. Now let us talk about a constant pressure isobaric or isopistic process. So now I would like to calculate the work transfer or in this particular process. Once again, to remind you, this equation which we are using, this we are using for a closed system. Okay, we are using it for a closed system. So you can see it here. This is the initial point from where the gas is, this is the initial coordinates or state of the gas. This is the final state of the gas, and this is a horizontal line. So along this line, pressure P1 is equal to pressure P2. So it's a constant pressure process. Now I will be using the same equation, delta W is equal to PdV. I can integrate it between 1 and 2 on both sides. Okay, so pressure being constant can be taken out of the integration sign. So dV remains inside the integration sign. When I integrate this dV, I will be getting V only, and I can write this value within the limits 1 to 2, and then finally I get PV2 minus V1, and I can multiply by P. So it is PV2 minus PV1. This is the expression for the work. Now once again, I have reached up to this particular point. W1 to 2 is equal to PV2 minus PV1. Okay. Now I know from the gas equation, PV is equal to mRT. So if it is V1 here, I can say temperature is T1. Similarly, if it is P2, PV2, then it can be written as mRT2. Okay, this is the gas equation. So I can instead of PV2 I can put here MRT2. Instead of PV1 I can put it here MRT1. MR being constant, common between both the terms. So this is taken out. We are left with T2 minus T1, and finally the expression for the work transfer in a constant pressure process is given by PV2 minus V1. This is the equation which is written here. So I have written it here first of all, and then this equation is written here mr t2 minus t1. So you need to remember these equations actually. This is very important.
Teacher,
Yes,
teacher,
yes.
can I replace M by N? PV minus 1 equal nRT.
You are talking
No,
about, I could understand. You are saying that you have studied PV is equal to nRT, isn't it?
yes, yes,
Where N is the number of moles, isn't it?
yeah,
It is
yes,
equal to number of moles. And this R which you are using in this particular equation is universal gas constant. Okay, universal
mm,
gas constant. Now there is a difference, not the difference. Both the equations are exactly similar. The difference is that when I say, when I write this particular equation, I say that this is U, R U. Okay, so either I write this R as R U, or I usually can use also R bar. And this term, both these terms are actually representing universal gas constant. But when I am writing this particular equation, PV is equal to MRT. Okay. Now this M is mass, and this R is not universal gas constant. Rather, it is characteristic gas constant. Characteristic gas constant. And the problem which I discussed earlier also, I told you there is a relationship between R bar. R bar is equal to molecular weight of the sub gas multiplied by characteristic constant. So this is the relationship I told you earlier also. When I solved a numerical problem on calculation of the mass of the hydrogen gas, we used only this particular equation, this equation. So for this particular course, you should forget this equation. Both are one and the same actually. Okay, there is no difference actually. Okay, because if
yes, yes,
you can also say that if you have to write m, m is equal to n into m. Okay, because unit for n is number of moles, so I can say mole, and this is molecular mass, so it is kg per mole. So mole and mole cancels out. So this is the relation. So when you will be using this relation in this particular equation, then you will get this particular equation. Okay.
yes. It means if I use that, I will find the same response.
See, you can use both the equations. I am not saying that, but it's now because you are in a engineering class, and we won't be dealing with the moles actually. Okay. See,
Yeah,
that you usually use in chemistry actually. Here we won't be using moles. Here we will be using the macroscopic property, which is mass actually. Okay. So you have to adjust yourself to this change actually. Okay.
okay, thank
So
you.
let us proceed to the next process. It is constant temperature or isothermal process. So you can see it here. In isothermal process, the temperature is constant, and I can write, this is once again the gas equation, PV is equal to MRT. Okay. Now you can see this term M and R are already constant for a gas. This is constant. If a gas is given to us, then this term is constant. And we say that isothermal process, so T also becomes constant. So total right hand side, this total right hand side is now constant. This is constant. So I get the equation PV is equal to constant. I can say P1 V1 is equal to P2 V2 is equal to P3 V3 and so on. Okay, is equal to Pn Vn, and this is equal to constant. Uh, and this is the actually this diagram shows the graph for figure for the constant temperature process. This is constant temperature process. Once again, using the same equation, delta W is equal to PdV. So integrating it both the sides, delta W from 1 to 2 and PdV from 1 to 2. Okay. Now we have to use some value of P so that I can integrate, because P cannot be integrated with dV actually. Okay. So from this particular equation, I can find out the value of P. P will be equal to C by V. So in the next here you can see I have replaced the value of P here. You can see it here. P is replaced by C by V. Now this C being constant can be taken outside the integration sign. So this on integrating I will get log V2 by V1. Okay, this is simple. And then this C will be equal to P1 V1 log V2 by V1. And this I have already told you that this is the process. PV is equal to constant. So P1 V1 is equal to P2 V2. So I can replace this P1 V1 by this P2 V2 also. So log V2 by V1. Then I can also write that because PV is equal to MRT. Okay, so I can write MRT1. I can also write MRT2 because both T1 and T2 are same. It's a isothermal process. Log V2 by V1. Instead of using V2 by V1 here, what I can do is I have found out the value of V2 by V1, which is equal to P1 by P2. So here I have replaced this value here by P1 and by P1 by P2. Okay, and this is P1 by P1 V1. This is already used here. Okay, and this has been replaced by P1 by P2. So actually, there are number of equations for which I can write for the isothermal process for work transfer. One is P1 V1 log natural V2 by V1. Okay, and this can also be written as P1 V1 log natural P1 by P2, and this term is equal to M R T1, or we can also write M R T2, and same here. Okay, so you can use any thing in this particular case. So I think it's 2:58 in my watch, so I will end this lecture here only. But I have sent one of the lectures which I have taken in A6 group, where one more process I have covered, which is reversible adiabatic. Okay, there are only 2-3 more slides for this particular process, 2 slides. So if you can see that lecture for this reversible adiabatic process, then you can understand this also. And in the next class on Monday, I will discuss about once again about this process and polytropic process. Okay, so if you have any questions, you can ask. Any questions?